In this slide, we will talk about the total numerical error. And up to now, we learned about the truncation error and also round-off error. This was chapter 4, this was chapter 3. And with the summation of these two, we will have a total numerical error. And for the round-off errors, you know that we have this because of chopping or omitting some numbers. And this can be reduced by increasing the number of significant figures that we show the numbers. And also the round-off error will increase due to the subtractive cancellation or increase of computations, because when we increase the computations with some omitted numbers, there will be a cumulative round-off error issue. And the truncation error can be reduced by decreasing the step size, because truncation error is because of the approximation method, let's say the Tyler series, for example. If we can reduce the step size, we learned this already, we can have a better prediction, so it will reduce the truncation error. However, a decrease in step size can lead to subtractive cancellation or to an increase in computations. That means the computational cost will increase, but still we will have an improved prediction, let's say. And also, the truncation errors are decreased as the round-off errors are increased. So this is an important fact as well, because we have subtractive cancellations and increased computations in the reduced step size. And we say that the round-off error will increase with the increase of computations. Here also increase in computations. That means decreasing the step size will increase the computations. It will increase the round-off error. So there's a chance of having round-off error because of decreasing step size, but it will also decrease the truncation error. So there's a trade-off. When you decrease the step size, you can decrease the truncation error, but can increase the round-off error. Here the important point is how big is the round-off error. If it is too small, then this is not really important. But if the round-off error is larger or comparable with the truncation error, then we need to think about this issue of having increased computations, which increases the round-off error. So based on the comments that we made in the previous slide, we will have this following dilemma. In a computation, we could conceivably decrease the step size to minimize the truncation errors, but the round-off error will start dominating the solution and the total error grows. And that's why our solution becomes our problem. So the solution is decreasing the step size to minimize truncation error. But as we said, decreasing step size will increase the computations, and the increase of computations will increase the round-off error. And at some point, you can see here a figure, at some point, the round-off error will be more dominant than the truncation error. So this is a problem. That's why we will have an optimal step size or an appropriate step size that we need to determine. We want to choose a large step size to reduce the amount of calculations and round-off error without having a large truncation error. So we also want to reduce the truncation error as well. So there's a big trade-off over here. If the total error is as shown in the figure, let's say this is the total error, the challenge is to identify the point of diminishing returns. So this is the point of diminishing returns actually, where round-off error begins to negate the benefits of step size reduction, because you can see the round-off error after some point begins to negate the benefits of step size. For such cases, a numerical uncertainty is defined, and we will show an approach about this in the following section. In this section, we will show an appropriate approach to be able to determine a suitable step size to have a solution for the trade-off of truncation error and round-off error changes based on the step size. And we will focus on the centered difference of first derivative for this purpose. Let's write it down to remember. Centered difference of first derivative. This is known as fxi. The derivative is actually it is just xi plus 1 function value minus xi minus 1 function value divided by 2h. And if you remember, we had a reminder term, and for this one it is, if we truncate it after the first term, which has a third derivative, it is h square. It is this value. So we can simply define these. This is the true value of differentiation or derivative, true value. This is finite difference. Approximation. And this is truncation error. So if there is no round of error, the only error is due to the truncation. Assume that we don't have any round of error, we only have this truncation error then. But for computers, there is always round of errors. So we need to determine the round of error. And for computers, or even in our calculations, we always have round of error. Meaning, for the function xi minus 1, we will have a prediction with truncation error, and also we will have a round of error. Let's show it by e minus 1. And for x, let me correct this as I, here also I plus 1 is equivalent to f xi plus 1 plus e I plus 1. And these are called round of errors. This e and this e are the round of errors. And these are, this one and this one are the rounded, let's show this way, and this one as well, rounded function values. So we calculated the function value and rounded it to a certain digits. Then we will have round of errors, which are shown by e values over here. So if we know this and this, or if we present fxi minus 1 and fxi plus 1 with these values, then over here we can substitute these values and have another definition of this. Let me show this way. Let's have this function or this center difference and substitute these. Substituting, then we will have the f xi derivative is equivalent to, for xi plus 1, we will have f xi plus 1, the rounded value, minus also xi plus 1 rounded value, I minus 1 rounded value, divided by 2h again. And then we will also have these, and we just separated them for a better demonstration. ei plus 1 minus ei minus 1 divided by 2h again, because they are the same actually. We just replace these to here. And the truncation error is the same. Just this value again over here. So you can see we will have then the finite difference approximation here. This is the round-off error. And this is the truncation error. And that's simple actually. We will just have the round-off error representation of the function values and write them here and get the combined round-off error and truncation error statements or expressions of the derivative, for example. This can be used for any kind of approximation method. This was only shown here for the standard difference approach. You can use this for forward difference, backward difference, or Taylor series, doesn't matter. You can use this for any of those. In this slide, we will have an example to show the combination of round-off and truncation errors and a demonstration of it with a MATLAB code, actually. So here in example 4.4, we used a standard difference approximation of or H² to estimate the first derivative of the following function. So this is the function. We use the standard difference to approximate first derivative of this at x equals 0.5. We will use the same starting with h equals 1, then reduce the step size by a factor of 10 to demonstrate how round-off becomes dominant as the step size is reduced. And we will also compare it with the true value, the real value of the derivative, which is this one. And we will use this in a MATLAB code. I will not show any hand calculations here. In a MATLAB code, we can show this. In the following slide, we have a MATLAB algorithm and the results. And let's move on to the next slide for this solution. So on the left-hand side, you have a MATLAB function to calculate the standard difference of a function. And we will use this with format long. And the f true is equivalent to the function value. The true value is calculated by the function value. Here we will have the step size starting from 1, and the difference value is actually x plus h and x minus h divided by 2h. We know this already mentioned. This is the standard difference function, and E1 is the absolute true minus D1 value. D1 is the prediction. The true value is this. And we will do this from I equals 2 to n. N is determined as an initial value, actually. So we can just divide h by 10 for n times, let's say. We can just define this by ourselves. And hi is also a vector of the step size values, just adding them into there, and we calculate all the function values and the absolute error values of difference of the true and predicted values, and finish the for loop so that we can calculate all the function values and errors, or all the derivatives and errors for each step size. Then we will have a matrix of these, and we will print this step size find difference true error. So these are actually the demonstrations of the values, and I will keep this short. You can just copy these and paste to MATLAB and see what these do. We actually want to plot the h and e. H is the step size, and e is the simply the error values. And on the right hand side, you can see the step size is reducing from 1 to a very small value at each step, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have only 10, n equals 10 reduction. The finite difference values, these are the d values, and the true error values, these are these values. And this is a function. Now you can just call this function using this m file simply, and in here we have the function. You can see at x we will simply solve this, and you can just copy and these to the command window of MATLAB, and it will call this over here, the x function, and give you the results. And we have n 11 actually, because I count 10, but with 1 it is 11, and 0.5 is the initial x value, and ff and df are the functions you can see over here. And we obtain these results when you actually run these commands with this function. So the center difference function also plots the error in terms of step size, as you can see over here. And we see that when the step size is large here and small here. And we started with 1 actually, and somewhere here. So with a large step size, the error is too much. But when we reduce the step size, the error is reducing, but after a while, the error starts increasing again. So this shows the exact problem that we mentioned earlier, the trade-off between the round-off and the truncation error by decreasing the step size. So at first over here, the round-off is minimal, or the truncation error is more dominant, let's say, it is larger. And that's why the total error equation is this. So we have the center difference and the truncation error. The total error drops by a factor of 100 each time. We divide this step by 10 because we have h square over here. But starting from 0.0001 step size, which is somewhere here, we see round of error begin to creep in and erode the rate at which the error diminishes. Basically, we see this result. So diminishes, and here, I mean, it's getting the error steepness is getting reduced, and at 10 to the power 8, it reaches to minimum. Then beyond this point, the error starts increasing. So we can choose a step size of either this or this value, because even here the round of error starting to be dominant. That's why the error decrease is reducing. So somewhere here we need to choose the step size according to this solution. And you can use the previous slides and MATLAB code to be able to get this kind of curves easily. Please try this in your free time as an exercise.